Yes. So we have come up to this point. Okay. So this is the stochastic trend. Stochastic trend means the trend itself is random. How to get this stochastic trend? In a random walk model, suppose your series looks like this: yt is equal to yt minus 1 plus epsilon t. If you follow the process of iteration, you can look at this series in this form: yt is equal to y naught plus sum of epsilon t minus I. What does it mean? That is, the value of y in period t is equal to its initial value y naught plus accumulation of the random shocks from the initial period. So by getting accumulation of the random shocks, you get the present value of y. Okay, so when shocks have been accumulated over time, you will get the trend in the series simply in the form of a stochastic, because shocks is stochastic by nature. That's why when phi 1 is equal to 1, that is in presence of a unit root, we have stochastic trend. Okay. Now, again consider the random walk model without drift. How to get this form? Just by setting phi naught equal to 0, phi 1 is equal to 1 in air 1. That is, we allow the presence of unit root. Phi 1 is equal to 1 means unit root, we have already explained. We are ignoring intercept. So the specification of yt looks like this. And if yt follows this process, it is non-stationary with unit root, or it is non-stationary exhibiting stochastic trend. Okay. Now, if we take the first difference of this series, your series is yt. If you take the first difference, the value looks like this: delta yt is equal to yt minus 1. So it is ultimately equal to epsilon t. So if we treat the first difference of the series as a separate series, so yt is your original series. If yt follows random walk, yt is non-stationary with unit root. But if we consider the first difference of the series, the value of the first difference is epsilon. And by assumption, epsilon is random walk. Epsilon is white noise. That is, epsilon t is purely random variable. So after taking first difference of the non-stationary series, it becomes stationary. Try to understand this point. If yt follows random walk, that is, if yt looks like this, it will be non-stationary. But if we consider the first difference of the series, it becomes stationary. Why? Because if you take first difference simply is equal to epsilon t, and epsilon t by assumption stationary. For this reason, the first difference of the random walk series is stationary. So we can interpret this model in this way: if yt follows random walk, yt originally non-stationary, but after taking first difference, yt becomes stationary. For this reason, this type of process is called different stationary process, DSP. Different stationary process means the series originally is non-stationary, but after taking first difference, it becomes stationary. Clear? So DSP means the series is originally non-stationary, but after taking first difference, it becomes stationary. So this is the story about AR1. So in AR1, think about the basic structure of AR1. Yt is equal to phi naught plus phi 1, yt minus 1 plus epsilon t. If we impose the restriction phi 1 less than 1, yt becomes stationary. We have derived the results in class. If we set phi 1 is equal to 1 in AR1, you have a random walk model. If phi 1 is equal to 1, you can show easily yt will be non-stationary with stochastic train. Phi 1 is equal to 1 means the series contains unit root. So if the series contains unit root, it exhibits stochastic train. Okay. Now let we extend our analysis for AR2. Consider AR2. So try to write down the expression for AR2 independently just by looking at this expression in your exercise book. So AR2 is specified as yt is equal to phi naught plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus epsilon t. Introduce lag operator here. After introducing lag operator, you have this kind of expression. Take all yt term in the left hand side. So you have this kind of expression. Yt into 1 minus phi 1l minus phi 2l squared is equal to phi naught plus epsilon t. As I have mentioned in the case of AR1, if you set this component equal to 0, 1 minus phi 1l minus phi 2l squared. So set this equal to 0. You have what is known as the inverse characteristic equation. So this is the inverse characteristic equation for AR2. If you set z is equal to 1 by L in this inverse characteristic equation, you have z square minus phi 1z minus phi 2 equal to 0. This expression is called the characteristic equation. So in AR2, the characteristic equation is quadratic. In AR1, the characteristic equation was linear. But in AR2, the characteristic equation is quadratic. So if we solve this quadratic equation, you have two roots. These two roots are called the characteristic roots. So in AR2, you have two characteristic roots. In AR1, you have only one characteristic root, z is equal to phi 1. So in AR1, you have only provision of single unit root because you have only one unit root, only one characteristic root. But in AR2, you have two characteristic roots. So if you solve this equation just by applying the Siddharacharya formula, so you get z is equal to phi 1 plus minus square root of phi 1 square plus 4 phi 2 divided by 2. So you have two values of z. One is suppose z1, another one is z2. So this is the value of the characteristic roots. And I have already mentioned, in the case of AR1, the value of characteristic root Z is equal to phi1, exactly similar. But in AR2, the value of Z is not equal to phi1 or phi2. So value of Z is equal to this kind. That is the combination of phi1 and phi2. So one value of the root is simply phi1 plus this term divided by 2. Another value of the root phi1 minus square root of this divided by 2. Okay. Now we are interested in the value of the characteristic roots equal to 1. Why? Because if the value of the roots equal to 1, we can say unit roots. So in the case of AR2, we have different type of situations. Situation 1, two roots Z1, Z2 both equal to 1. Suppose that here you can get the value of Z. By solving it, suppose you get both the values equal to 1. Z1 is equal to 1, Z2 is equal to 1. So if Z1 is equal to 1, Z2 is equal to 1, there are two unit roots. That is, when both the roots are equal to 1, we can say YT in AR2 contains two unit roots. And if YT contains unit roots, it will be non-stationary. We have already shown in the case of AR1, if a series contains unit root, it will be non-stationary with stochastic train. So it will also be applicable for AR2. So in AR2, if Z1 is equal to 1, Z2 is equal to 1, that is both roots are equal to 1, the series will contain two unit roots, and in that case, YT will be non-stationary, exhibiting stochastic train. So you have to mention this part because non-stationary may be of different types. Non-stationary with stochastic train, non-stationary without stochastic train. So for that reason, to understand the behavior of non-stationarity in presence of unit root, you have to mention this term non-stationary with stochastic train. So this is one case. Another possibility in the case of AR2. In the case of AR2, you have quadratic characteristic equation. So you have two characteristic roots. In the second alternative, suppose Z1 is equal to 1 and Z2 less than 1. Or Z1 less than 1 and Z2 is equal to 1. In other words, out of the two roots, one root is equal to 1, another root less than 1. So if this is the case, the series YT will contain one unit root. And still, YT will be non-stationary, exhibiting stochastic train because it contains one unit root. Another possibility in the case of AR2, both the roots are less than 1. If both the roots are less than 1, there is no unit root. And in this case, the series YT following AR2 will be stationary. So stationarity means, stationarity condition, we can say alternatively, stationarity means the value of the characteristic roots should be less than 1. So if the value of the characteristic roots less than 1, the series will be non-stationary. You can understand it just by conceptualizing the case of AR1. In the case of AR1, YT is not stationary when phi1 less than 1. In the case of AR1, phi1 is the characteristic root, Z. So the series YT, even in the case of AR1, is stationary when the value of the root is less than 1. So we can generalize this result for all autoregressive process in this way. the autoregressive process will be stationary when the characteristic roots involved in the series are less than 1. Okay. So in AR2, you have 3 different situations. One situation, both the roots is equal to 1. And in this case, we can say the series will contain 2 unit roots. In second alternative, value of the one root is equal to 1 and the other root less than 1. In this case, the series contains 1 unit root. In alternative 1, alternative 2, both cases, YT will be non-stationary with stochastic train. But the nature of non-stationarity in case 1 and case 2 will obviously be different. Why? Because in case 1, you have 2 unit roots. In case 2, you have 1 unit root. So in case 1, YT exhibits stochastic train where there are 2 unit roots in the series. While in case 2, the series exhibits stochastic train containing only 1 unit root. So obviously, the type of stochastic train in case 1 and the type of stochastic train in case 2 will be different. But both are non-stationary. In case 3, when the both roots less than 1, the series will be stationary. Okay. Now, let me consider the case 1. That is, if both roots are equal to 1. If both roots are equal to 1, that is Z1 is equal to 1, Z2 is equal to 1. In this case, we have sum of the roots. You know, if you rethink the basics of theory of quadratic equation, sum of the roots is equal to minus b by a, and the product of the roots is equal to c by a. By following this rule, we can say sum of the roots z1 plus z2 is equal to minus b by a, means in our case phi 1. And product of the roots z1 into z2 is equal to c by a in general, but in our case it is equal to minus phi 2. Okay, so this result and this result we have got by utilizing the theory of quadratic equation. Now, when both roots are equal to 1, if z1 is equal to 1, z2 equal to 1, so obviously phi 1 will be equal to 2 and phi 2 will be equal to minus 1. Okay, so think about the basic structure of AR2. How do we express AR2? AR2 is expressed in this way: yt is equal to phi naught plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus epsilon t. So in this expression, if the value of phi 1 is equal to 2 and the value of phi 2 is equal to minus 1, in other words, if the series yt looks like this, yt is equal to phi naught, whatever may be the value of phi naught, yt is equal to phi naught plus twice yt minus 1. Why twice yt minus 1? Phi 1 is equal to 2. Minus yt minus 2. Why minus yt minus 2? Because phi 2 is equal to minus 1. So if phi 2 is equal to minus 1, phi 1 is equal to 2, or if yt is equal to phi naught plus twice yt minus 1 minus yt minus 2 plus epsilon t, then yt will contain 2 unit roots. So in the case of AR1, we have got unit root means phi 1 is equal to 1. That is, the coefficient of yt minus 1 is equal to 1, indicates the presence of unit root in AR1. But this is not the case for AR2. In the case for AR2, yt will contain 2 unit roots when phi 1 is equal to 2. That is, the coefficient for yt minus 1 is equal to 2. And the coefficient for yt minus 2 is equal to minus 1. Okay, so we have to keep in mind the concept of unit roots not directly related to the value of phi 1, phi 2, etc. The concept of unit root is directly related to the concept of characteristic roots. If the characteristic roots involved in a series equal to 1, then we can say the series contains unit root. If the series contains unit root, it will be non-stationary with stochastic train. Clear? So in the case of AR2, as we have number of characteristic roots is equal to 2. So in AR2, you have the possibility of maximum unit root 2. So in the case of AR2, you have the number of unit roots is equal to 2 or is equal to 1 or is equal to 0. When both Z1 is equal to 1, Z2 is equal to 2, number of unit roots is equal to 2. If Z1 is equal to 1, Z2 less than 1, or vice versa, number of unit roots is equal to 1. If both Z1 less than 1, Z2 less than 1, number of unit roots equal to 0. So in AR2, you have three possibilities. So the AR2 series YT may be of three types. Type 1, YT may contain 2 unit roots. In this case, YT will be non-stationary with stochastic trend. YT may contain 1 unit root. In this case also the series is non-stationary with stochastic trend. If YT contains no unit root, YT in AR2 will be stationary. So YT in AR2 will be stationary if the value of the characteristic roots are less than 1. Okay, so you have used the concept of the roots, characteristic roots earlier in calculating autocorrelation function, etc., or in analyzing the behavior of AR2 series in general. So we can look at the stochastic behavior of a series by utilizing the concept of unit root, by utilizing the concept of characteristic roots equal to 1 in an alternative manner. Okay. Now, let we generalize further the autoregressive process of order P. Write down this expression. ARP is expressed in this way: YT is equal to phi naught plus phi 1 YT minus 1 plus phi 2 YT minus 2 plus up to phi P YT minus P plus epsilon T. So this is the general expression for ARP. Introduce lag operator just by following the case of AR2. Do it yourself independently. I have not shown here. So this is the expression for AR2. Introduce lag operator. So the expression becomes YT is equal to phi naught plus phi 1 L YT plus phi 2 L square YT plus in this way phi P L to the power P YT plus epsilon T. If you take all YT components in the left hand side and if you take YT as a common factor, within bracket you have 1 minus phi 1 L minus phi 2 L squared minus dot 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 up to minus phi P L to the power P is equal to, in the right hand side, phi naught plus epsilon T. So in the case of ARP, the expression multiplying with yt, 10 minutes remaining, multiplying with yt, you have the expression within bracket, and it is a polynomial of order p because it starts with 1 minus phi 1l minus phi 2l squared minus up to phi p l to the power p. Set this expression equal to 0. You have inverse characteristic equation relating to ARP. And again, if you set 1 by L is equal to Z, you have a characteristic equation looks like this. Z to the power P minus phi 1 into Z to the power P minus 1 minus phi 2 into Z to the power P minus 2, in this way minus phi P equal to 0. And you can easily understand the solution of this characteristic equation is not easy as in the case of quadratic equation or linear equation. In the case of linear equation, you can get directly the value of the root. In the case of quadratic equation, you can get the value of the roots by applying Siddharacharya. But in this case, you can get the value of the roots in other way. One possible way, just express this polynomial in a multiplicative factor like this. So suppose this expression is denoted by this symbol phi of z. So phi of z indicates phi of z equal to 0 is the characteristic equation for ARP. Okay, phi of z actually is equal to this. The structure of phi of z is equal to z to the power p minus phi 1 z to the power p minus 1 minus up to phi 2 z to the power p minus 2. In this way, last term is phi p minus phi p, this equal to 0. Now suppose this polynomial can be factorized in this way, z minus 1 into the rest component, and the rest component we have denoted here by phi star z. So suppose phi of z means this is equal to z minus 1 into phi star z. How to get it? Just by taking the factor z minus 1, if we can express this in this form. So obviously, this part of the polynomial phi star z will be a polynomial of order p minus 1 because phi of z is originally of order p. So we have taken one z outside. So if we take one z outside, the remaining part will be a polynomial of order p minus 1. So if you can express this polynomial in this form, by solving this, you have z equal to 1. So if you express phi of z is equal to this, so you can write either z minus 1 equal to 0 or this component equal to 0. So z minus 1 equal to 0 indicates one value of the root equal to 1. So here the ARP contains one unit root, and the series will be called integrated of order 1. When a series contains one unit root, we can say the series will be integrated of order 1. It is not only for ARP, it is applicable for a series following any order of autoregression. In AR2 also, in AR1 also. In AR1, you have only one possibility because in AR1, you have only one characteristic root. So you have a possibility of only one root. So AR1 may be integrated of order 1 or stationary. In AR2, you have three possibilities. In AR2, when the series contains two unit root, it will be integrated of order 2. If AR2 contains only one unit root, it will be integrated of order 1. If AR2 contains no unit root, that is, if AR2 is stationary, it will be integrated of order 0. So any stationary series can be said integrated of order 0. Okay. So remaining time shows 4 minutes. So it will be interrupted again. So we can start afresh after 4 minutes. Okay. So till now we can continue. Now, so here we have only one unit root. Similarly, if we can express the characteristic equation for ARP in this format, phi of z is the polynomial of order p. We can factorize this polynomial in this way, phi of z minus 1 whole square into the rest component. So in the rest component, the polynomial will be of order p minus 2. So if you can express the characteristic equation in this form, then ARP will contain 2 unit roots. So we impose here if. So if the characteristic equation looks like this, by solving it, we have 2 roots equal to 1. And in this case, the ARP module will be integrated of order 2. Okay. In this way, suppose the characteristic equation looks like this: z minus 1 whole to the power d into phi to the power d z of z. That is, we can take z minus 1 whole to the power d and the rest component, this part, equal to 0. So in this part, the rest component will be the polynomial of order p minus d, because we have taken z to the power d outside. So the remaining part will be a polynomial of order p minus d. So if you can express the polynomial function in this way, the ARP will contain d unit roots, because here z minus 1 whole to the power d. So by solving it, you can d number of z equal to 1. So here the ARP contains d unit roots, and in this case it is called integrated of order d. Okay. So this is about non-stationarity with unit root. Now non-stationarity without unit root. So it will end after 1 minute 50 seconds. So can I start it, or after starting again?
Sir, don't start. Sir, don't start.
No, it's not. Start it.
Okay, so we can continue. So non-stationary without unit root. Just try to remember our initial points. Initially, we have mentioned non-stationarity means trend in mean, or trend in variance, or trend in both. Trend in variance is similar to non-stationary with unit root. So if non-stationarity appears because of trend in mean value only, then we can say the non-stationarity without unit root. So in the case of non-stationarity without unit root, the series exhibits only deterministic trend. So no stochastic trend in this case. Okay. So we will discuss this point after starting again, because we have a very few seconds left